Hi everyone, good morning to our lecturer and my fellow classmates. Today, I'm going to present my Fluid Mechanics 1 assignment in this video here. I'm Kishanraj Analaki S. Kumar. My matrix number is 205715. So let's get into the video. First and foremost, we have 4 panels with us to discuss the fluid properties and dimensional analysis and modeling. So, panel 1, you can start your discussion now. Hi everyone, today we're gonna study about introduction to fluid properties. So the properties of fluid are density, specific weight, specific gravity, viscosity, capillary action. So the density is the amount of mass per unit volume. The formula is rho equal to m over v. The unit is kg over m cube. Specific weight is the amount of weight per unit volume of a substance. And the formula for specific weight is equal to W over V. The unit is N over N cube. So the next property is specific gravity. Specific gravity is the ratio of density of substance to density of water at 4 degrees Celsius. It's also defined as the ratio of the specific weight of substance to specific weight at 4 degrees Celsius. So the next property is viscosity. Viscosity is the property that represents the internal resistance of a fluid motion. The higher the viscosity, the higher the resistance of fluid towards motion. So one of the type of viscosity is kinematic viscosity, which is the ratio of dynamic viscosity to the density of fluid. So the unit for kinematic viscosity is m square over s. So the last property is capillary action, which is the ascension of liquid through slim tube, cylinder, or permeable substance due to adhesive and cohesive forces interacting between the liquid and the surface. So the next part that we're going to study about is Newtonian fluid and non-Newtonian fluid. Newtonian fluid is the one with a constant viscosity with zero shear rate. At zero shear rate, it's directly proportional to the shear stress, which is independent on the shear rate, and it obeys Newton's law of viscosity. This Newtonian fluid have a linear relationship between viscosity and shear stress. So the example of fluid is water, mineral oil, gasoline, and alcohol. Now we can move on to non-Newtonian fluid. Non-Newtonian fluid is the one with the viscosity not constant, and is dependent on the shear rate, and it also does not obey Newton's law of viscosity. So the behavior of the fluid can be described one of 4 ways. The first behavior is dilatant, which is the viscosity of the fluid increases when shear is applied. For example, is quicksand, corn flour, and water. The next behavior is pseudoplastic. Pseudoplastic is the opposite of dilatant. The more shear stress is applied, the less viscous it becomes. Example is ketchup. The another behavior is rheopactic, which is very similar to dilatant in that when shear is applied, viscosity increases. The difference here is that viscosity increase is time dependent. Example is gypsum paste and cream. The last behavior is thixotropic, which is fluid with thixotropic properties decrease in viscosity when shear is applied. This is a time-dependent property as well. For example, paint, cosmetic, asphalt, and glue. Thank you, panel 1. Next, panel 2, could you share your discussion with us? So the next part that we're going to study is surface stretch and elastic modulus. So the greater the stress, the greater the strain. However, the relationship between stress and strain does not need to be linear. Only when stress is sufficiently low is the deformation it causes the direct proportion to the stress value. The proportionality constant in this relation is called as the elastic modulus. So the equation is elastic modulus is equal to stress over strain. We can also see that from that when an object characterized by a large volume of elastic modulus, the effect of stress is small. On the other hand, the small elastic modulus means that stress produces larger strain and noticeable deformation. For example, a stress on a rubber band produces larger strain than the same stress on a steel band of the same dimension, because the elastic modulus for rubber is 2 orders of magnitude smaller than the elastic modulus for steel. So the elastic modulus for tensile stress is called Young's modulus. So Young's modulus is meaningful only in the range in which the stress is proportional to the strain, and the material returns to its original dimension when the external force is removed. Okay, so the next part that we're going to study is compressibility of fluid and vapor pressure. Compressibility of the fluid is characterized to shrink in volume when increasing the external pressure. It also defined as the measure of the relative volume change of a fluid as a response to a pressure. The fluid expands when heated or depressurized, and the fluid contracts when cooled or pressurized. Okay, now we can go to vapor pressure. Vapor pressure is a measure of the tendency of a material to change into gases or vapor states, and it increases with temperature. The temperature at which the pressure at the surface of a liquid becomes equal to the pressure exerted by the surrounding is called the boiling point of the liquid. The pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases, solid or liquid, at a given temperature in a closed system. The equilibrium vapor pressure is an indication of a liquid evaporation rate, and is related to the tendency of a particle to escape from the liquid. A substance with a high vapor pressure at normal temperature is often referred to as volatile. The pressure exhibited by vapor present above a liquid surface is known as a vapor pressure. As the temperature of a liquid increases, the kinetic energy of its molecule also increases. As the kinetic energy of the molecule increases, and the number of molecules transitioning into a vapor also increases, thereby it increases the vapor pressure. That's all from me. Thank you. Thank you, panel 2. Next, panel 3, you can start your discussion now. The next part is dimensional analysis and modeling. The topics that we're going to study here is dimensions and dimensional homogeneity. Dimensions are a measurable extent of some quantity such as length L, time T, mass M, and etc. Units are labels for different dimensions and combination of dimensions such as kilograms and Newton. So now the dimensional homogeneity is the concept where the dimension of variables on both sides of the equations are the same. If units are the same, the dimension of each term must be the same. Every valid equation must be dimensionally homogeneous. That is, all additive terms on both sides of the equation must have the same dimensions. Example of dimensionally homogeneous equation is length equal to length over times time. So an equation could be dimensionally homogeneous but invalid if the equation is also not fully balanced. For example, L equal to L plus L. This is example of equation that is dimensionally homogeneous. That's all from me. Thank you. Thank you, panel 3. Last but not the least, panel 4, you can share your discussion with us now. The next part that we're gonna study is dimensional analysis and similarity. Dimensional analysis is very useful for planning, presentation, and interpretation of experimental data, and is a method for reducing the number and complexity of experimental variables that affect a given physical phenomena. For example, suppose the F force on a particular body shape immersed in a stream of fluid depends only on body length, velocity, fluid, and viscosity. For dimensional similarity, there's 3 types of dimensional similarity: geometrical similarity, kinematic similarity, and dynamic similarity. Geometrical similarity is established when a model and prototype are geometrically similar if and only if all body dimension in all 3 coordinates have the same linear scale ratio. And kinematic similarity, it requires that the model and prototype have the same length scale ratio and same time scale ratio, thus the velocity scale ratio will be same for both. And for the dynamic similarity exists when the model and the prototype have the same length scale ratio, time scale ratio, and force scale ratio. So the next topic that we're gonna study is the method of repeating variables and the Buckingham's pi theorem. Buckingham's pi theorem states that if there are n variables in a problem and these variables contain m primary dimensions, the equation relating all the variables will have nk, which is the dimensionless group. So n is dimensional variable and m is minimum number of dimension to describe the variables. In this method of solving the equation, there are two conditions. Each of the fundamental dimension must appear at least one of n. It must not be possible to form a dimensionless group from one of the variables within a recurring set. A recurring set is a group of variables forming a dimensionless group. So I have a sample question here.
Question is, the pressure drop delta P along a straight pipe of diameter d has been experimentally studied, and it is observed that for a laminar flow of a given fluid and pipe, the pressure drop varies directly with the distance L between pressure taps. Assume that delta P is a function of d and L, the velocity v, and the fluid viscosity mu. Use dimensional analysis to reduce how the pressure drop varies with pipe diameter. So the first step we have to do is list all the variables that are involved in the problem. Delta P is equal to F, which is dLv mu. So step 2, we have to express each of the variables in terms of basic dimensions. So we have to list down all the variables and it is units. So from the unit we can do the dimension. So the step 3 is determine the required number of pi terms. So we already know n is equal to 5. So 5 is delta P, D, L, V and mu, and m is equal to 3 because we have 3 dimension, which is m, L, T. And then we have to find the r. R is n minus m, which is equal to 2. Hence we can conclude that it has 2 pi terms. Okay, now the step 4. Step 4, we have to select a number of repeating variables where the number required is equal to the number of reference dimensions. For this question is m equal to 3. All of the required reference dimension must be included within the group of repeating variables, and each repeating variable must be dimensionally independent of the others. And the third point is, do not choose the dependent variable as one of the repeating variables, since the repeating variables will generally appear in more than one pi term. So we have dv mu, so its dimensions is L, T, M respectively. So step 5 is we have to combine this dv mu with one additional variable, which is a delta p or L, in sequence to find the two pi products. First we will do delta p. So pi 1 is equal to d power of a, v power of b, mu power of c, and we have to times with the delta p. So we will get m, so we will have to substitute it with dimensions. So m power of c plus 1, L power of a plus b minus c minus 1, and t power of minus b minus c minus 2. So it will be equal to m power of 0, L power of 0, and t power of 0. From this we can equate the exponents and we can do the equations. So c plus 1 is equal to 0, a plus b minus c minus 1 is equal to 0, and minus b minus c minus 2 is equal to 0. And if we solve all this simultaneous equation, we will get a equal to 1, b equal to -1, and c equal to -1. So therefore, we will get pi1 is equal to delta p d over mu v. Okay, step 6, we have to repeat the step 5 for each of the repeating, non-repeating variable. So we have to times with L now. So d power of a, v power of b, mu power of c times L. So if we substitute with the dimension, we will get m power of c, L power of a plus b minus c plus 1, and t power of minus b minus c. So it is equal to m power of 0, L power of 0, and t power of 0. So we have to equate the exponents into these equations. C equal to 0, a plus b minus c plus 1 equal to 0, minus b minus c equal to 0. So if we solve this simultaneous equation, we will get a equal to -1, b equal to 0, and c equal to 0. So therefore, we will get pi 2 is equal to L over d. Okay, now step 7. Step 7, we have to check all the resulting pi terms. And one good way to do is to express the variables in terms of FLT, if basic dimension MLT were used initially or vice versa. So um, we have to list down all the variables, units, dimensions. From this we will get pi1 is equal to f power 0, L power 0, and t power 0. So pi2 also same, it will be f power 0, L power 0, and t power 0. Okay, step 8, the last step. So we have to express the final form as a relationship among the pi terms. So pi1 is equal to f by pi2. So pi1 we already know, the pi1 is equal to delta pd over mu v, and it's equal to f over L over d, which is the pi2. So we have to, since the delta p is directly proportional to L, we can conclude that delta pd over mu v is equal to c dot L over d, where c is a constant. Thus delta p directly proportional to 1 over d square. Okay, where we get d square is from the d from the left side will move to the right side, so it will become 1 over d square. And that's how we have to solve this kind of questions.
So the last part that we're gonna study is dimensionless term. In dimensional analysis, a dimensionless quantity is a quantity without any physical units and thus a pure number. Such a number is typically defined as a product or ratio of quantity which do f units and in such a way that all the units cancel out. So an example is dimensionless numbers, which is the pi is a dimensionless number representing the ratio of the circumference of a circle to its diameter. That's all from me. Thank you. Thank you, panel 4. So that's all from us. Thank you for attending this discussion with us today. Hope you guys enjoy watching this video. Thank you.